pKa, pKb, the concept of pH, pOH, right? And uh, the buffer solutions. Okay, so what is this buffer? Buffer is nothing but a solution which resists change in its pH value. A solution which resists change in its pH value on addition of a small amount of either acid or base to it, that is called a buffer solution. Okay, and these buffers have a tendency to maintain their pH values. Okay, so a natural example of buffer is the human blood. Human blood is a kind of natural buffer which resists the change in its pH value. The pH of this natural buffer, that is called human blood, is slightly alkaline, that is 7.35. So buffer is nothing but a solution which resists change in its pH value. Okay, buffer is a solution which resists change in its pH value on addition of a small amount of acid or base in the solution. Then the next point is buffer index. So buffer index, what it is exactly? We know that buffer solutions are the solutions which resist change in their pH value. Buffer solutions are the solutions which resist change in their pH value on addition of a small amount of acid or base. But if a large quantity, excess amount of acid or base is added, then pH of that buffer solution may get changed. pH of that buffer solution may get changed. And whatever is the ratio, that is the concentration of strong electrolyte or base added divided by change in the pH value, concentration of strong acid or base added divided by change in the pH value, that is dB upon dpH, that is called buffer index. That is called buffer index. And this buffer index is a measure of quantitative measure of buffer capacity. Now what is that buffer capacity or what is the buffer action? We will see in the next slide. So up till now what we have seen? We have seen that buffer is a solution which resists change in pH value on addition of small amount of acid or base to it, that is called a buffer solution. These buffers have a good ability to maintain their pH even though a small amount of acid or base is added to it. So buffers are the solutions which resist change in their pH value on addition of a small amount of acid or base. And natural example of this buffer is this human blood. Our human blood is having pH in the range of 7.35. It is slightly alkaline in nature. See what will be the situation if the pH of buffer of this natural buffer, say human blood, would be changing from time to time. We, in normally human activities, we eat a lot of food. That food may be slightly alkaline, may be acidic in nature. And if we are taking this food in our blood, that would have increased the pH, changed the pH, and therefore all the metabolic processes which are taking place even in our human body, they may get changed, they may get disturbed. But this doesn't happen. See, the God has given us this buffer solution in our blood. So the pH of that buffer solution, that is the human blood, is 7.35. Okay, so this was regarding a buffer and what is buffer index. So buffer solution, pH of the buffer solution will not change if we add a slight amount of strong acid or strong base into that. But it may change if a large excess of acid or base is added, and when that concentration of acid or base added divided by change in the pH value, that is called buffer index. And this buffer index is a measure of buffer capacity or buffer action. Now here we will see what are the two different types of buffers. Buffer or buffer solution. We generally abbreviate the term buffer or buffer solution. So what are the types of buffer solutions? See, buffer solutions are of two types. One is called the acidic buffer and another one is called basic buffer. So both the types are nothing but equimolar mixtures of two things. So which are they? We will see. So an acidic buffer is a buffer solution containing an equimolar quantities of weak acid and its salt with strong base. Say, if we consider the equimolar quantities of weak acid, let us suppose acetic acid. So equimolar quantities of acetic acid, if it is mixed with equimolar amount of sodium acetate, then it will comprise this acidic buffer. Or if we take formic acid, a mixture of equimolar amount of formic acid and sodium formate, then that will constitute again an example of acidic buffer. So by an acidic buffer, we mean equimolar mixture of weak acid and its salt with strong base. The pH of this buffer lies in the range of acidic range. That is, we know that Sorensen has given a pH scale where he has divided the pH scale into three segments. One is the acidic range, one is neutral pH, and third one is the alkaline or basic pH range. If the pH of the solution varies in the range of 0 to 7, then we say that it is acidic buffer. It is acidic solution. If pH of the solution is exactly 7, we say that solution is neutral. If the pH range of the solution is 7 to 14, then we say that it is a basic solution. So by an acidic buffer, we mean a buffer solution consisting of equimolar quantities of weak acids and its salt with strong base. And that is called an acidic buffer. So we can have different examples. So acetic acid mixed with equimolar amount of sodium acetate, that will be an example of acidic buffer. See, these acidic buffers are having pH in the range of 0 to 7. These have pH in the range of 0 to 7. And pH of this acidic buffer is given by this relation, that is called pH is equal to pKa plus log of concentration of salt upon concentration of acid. See, what is this acidic buffer? It is nothing but equimolar mixture simply. It is an equimolar mixture of weak acid and its salt with strong base. Okay, so pH of the solution is in acidic range, that is in between 0 to 7, and it is given by a very well known and famous equation known by name of scientist, that is called Henderson. So acidic buffer can be calculated, pH of acidic buffer can be calculated with the help of Henderson equation. So this equation is called Henderson equation, that is pH is equal to pKa plus log of concentration of salt upon concentration of acid. Now once you see this term, that is acidic buffer, then the remaining term, that is alkaline buffer or basic buffer, is quite simple. So just take opposite of it. Right? So what will be there? Let us look at. So now as we know here, acidic buffer is a solution, equimolar solution containing equimolar amounts of weak acid and salt with strong base. See, example, this acidic buffer is calculated. Okay, and what is the pH range of this acidic buffer? Now a basic buffer is a solution containing equimolar amounts or equimolar quantities of weak base and its salt with strong acid. See, the definition has been reversed now. In acidic buffer, the weak electrolyte is weak acid. In basic buffer, the weak electrolyte is weak base. Okay, so a basic buffer is a solution containing equimolar amounts of weak acid and its salt with strong. A basic buffer, it consists of an equimolar quantities of weak base and its salt with strong acid. Say for example, ammonium hydroxide is a weak base. So if I take ammonium hydroxide and if I make it with ammonium chloride, this ammonium chloride is nothing but salt of this base ammonium hydroxide with strong acid, that is HCl. So a basic buffer is a buffer solution consisting of equimolar amounts of weak base and its salt with strong acid. Okay, and its salt with strong acid. Now the pH of these buffers is in the range of 7 to 14. pH of this basic buffer is in the range of 7 to 14. And Actually, here we define pH of acidic buffer. For basic buffers, we define POH. So what would be that? What would be that? That would be POH, that is equal to pKb plus log of concentration of salt upon base. Okay. In a similar way, we can define the POH of basic buffer. POH of the basic buffer is in the pH range, that is 7 to 14. It is calculated by this equation, that is called POH, that is equal to pKb. Okay, so I hope you remember the last equation. What was that? pH of acidic buffer. Okay, pH of acidic buffer, that was given by pKa plus log of concentration of salt upon concentration of base, that is weak base. Right? So, sorry, here weak acid. Just a minute. I am writing the previous equation here. Okay, so pH of acidic buffer, that is given as pH is equal to pKa plus log of concentration of salt upon concentration of weak acid. Here the relation for the POH, calculating the POH of this basic buffer is POH is equal to, so here instead of this pH, POH concept is there. Instead of this pKa, pKb concept is there. Instead of this, so salt concentration is remaining as such in the numerator, and in the denominator side, instead of this acid in the previous equation, here base term is there. Okay, so for any buffer solution, we can calculate pH of that buffer solution by using these two equations, and these two equations are nothing but the very famous equation that is known as Henderson equation. So in the next slide we will see what is this Henderson equation. Right? So this was regarding the buffer, okay, and the two types of buffers, that is called acidic buffer and another one is called basic buffer. Okay, I hope this concept is clear to you. Now there is one more term, that is called buffer capacity or buffer action. What is this term exactly? What this term is exactly, let us look into. Now, as I have given you the definition of either buffer solution, I have given you the definition of buffer solution, that is called, the buffer is defined as a solution which resists to change in its pH value. Now how exactly it does this action? How exactly it works to resist change in its pH value? That ability of that buffer solution to resist change in its pH value on addition of a small amount of acid or base, that is called buffer action or buffer capacity. So buffer action or buffer capacity is a mechanism how that buffer solution resists change in its pH value on addition of a small amount of acid or base. Means if I am trying to change pH of that buffer solution, it will not allow to change pH of the buffer solution. The buffer solution will not allow to change in its pH value on addition of small amount of acid or base, and that particular mechanism, that particular ability of that buffer solution to resist change in its pH value on addition of a small amount of acid or base, that is called buffer action or buffer capacity. So our next point will be how this buffer solution tries to resist change in its pH value when some small amount of acid or base is added to that. Okay, so here let us consider the action of acidic buffer and then we'll consider the action of basic buffer. Now what is this acidic buffer? As we have discussed in the earlier section, that this acidic buffer is nothing but an equimolar mixture of weak acid and its salt with strong base. So let us have an example of this acidic buffer. So let us consider an example of this acidic buffer which consists of a mixture of weak acid, say acetic acid, and its salt with strong base, that is, let us consider sodium acetate. So in this now buffer solution, what is there from the chemistry point of view? So this buffer solution will consist of two dissociations in the solution. See, this acetic acid is a weak electrolyte. It will dissociate only to a small extent. It will dissociate only to a small extent, so that the dissociation of this acetic acid can be expressed in this way. That is, acetic acid partial dissociation, incomplete dissociation, that is shown by this reversible arrow. That is shown by this reversible arrow. So this acetic acid is a weak electrolyte. It will dissociate into very small amount of H plus ions and acetate ions. But this sodium acetate is a salt, and we know that salts are near about 100% dissociated when they are dissolved. So as the name itself indicates, that acidic buffer is a equimolar, is a amount of weak acid and its salt with strong base. So let us have the example of acetic acid and sodium acetate. Now in this acidic buffer solution, there will be two kinds of dissociation. The first dissociation will be an equilibrium between the dissociation of these undissociated acetic acid molecules and the dissociated molecules. Okay, so acetic acid will dissociate into acetate ions and H plus ions. At the same time, there will be dissociation of the sodium acetate also. So sodium acetate will dissociate into acetate ions and Na plus ions. Remember here, this is an weak electrolyte. Acetic acid is a weak electrolyte. So the number of H plus ions and the number of acetate ions which are released from this acetic acid are quite less in number. But this solution will contain a large amount of acetate ions which are obtained by dissociation of sodium acetate. So this acidic buffer, now there will be a large amount of acetate ions, sodium ions, and undissociated acetic acid molecules. So if we look into this buffer solution will contain large amount of undissociated acetic acid, because this is weak electrolyte. So it will contain large amount of acetate ions, sodium ions, and undissociated acetic acid molecules. So in this buffer solution, there are a large amount of acetate ions. There are large number of acetate ions. And buffer capacity or buffer action is what? It is nothing but ability or tendency of that buffer solution to resist change in its pH value on addition of small amount of acid or base. So let us see what happens if we add some acid that consists of H plus ions, or if we add some base that consists of OH minus ions to this buffer solution. So if we add H plus ions, if we add some acid, so if a small amount of acid is added to this buffer solution, let us have the first situation where some small amount of acid is added. To this buffer solution, what will be the fate of the solution? So if small amount of acid is added, means ultimately I am adding H plus ions into that solution. So if H plus ions are added, what will happen? These H plus ions will react with the large amount of these acetate ions which are present in the solution. So even though we add quite large excess of this acid, what will happen? The H plus ions from the added solution will combine with these acetate ions, and they will produce acetic acid. So this neutral molecule will not change the pH. will not change the pH. So if a small amount of acid is added, then what will happen? The H plus ions which are added from the acid will combine with the acetate ions to form undissociated acetic acid molecules, and therefore pH of the solution does not change. pH of the solution does not change, and this is called reverse basicity of the solution is due to acetate ions. The solution is changing its nature, is trying to maintain its nature because of tendency of the large amount of those acetate ions which are present there. If we add some acid, the H plus ions from the acid molecule, H plus ions from the added acid will combine with the acetate ions, and it will be forming these undissociated acetic acid molecules, and pH of the solution does not change. Now the next situation is if we add a small amount of base. Okay, we know that according to Arrhenius theory, an acid is a substance which consists of H plus ions and base is a substance which consists of OH minus ions. More accurately, according to Arrhenius theory, acid is a substance which when dissolved in water produces H plus ions, and base is a substance which when dissolved in water produces OH minus ions. So if we try to add some base, means if we are trying to add some base, means some OH minus ions, so what will happen? What will happen? The OH minus ions, the OH minus ions from the added base, they will try to combine with this H plus ions which are there in the solution. So the H plus ions from this buffer solution will combine with the OH minus ions which are being added from the added base. They will form undissociated water molecule. See, again undissociated water molecule is formed. So at that time what will happen? The H plus ions are now consumed from the solution, right? H plus ions are now consumed from the solution because they are reacting with the added base OH minus ion. They are forming neutral water molecule. So pH of the solution will not change. Again, in order to restore the concentration of these H plus ions, in order to restore the concentration of these H plus ions, dissociation of acetic acid increases. Why? That is because of Le-Chatelier's principle. That is in accordance with the Le-Chatelier's principle. So for a acidic buffer, if we try to add some acid, the H plus ions from the acid will combine with the acetate ions which are large in number because of the dissociation of that sodium acetate. So it will be combining to form these undissociated acetic acid molecules, and therefore pH of the solution will not change. Therefore pH of the solution will not change. When we try to add some base, the base, it means it consists of OH minus ions. The OH minus ions which are added from the base, they will try to combine with the H plus ions, and they are forming these neutral water molecules. As a result, what is being done in the system now? What is being done in the equilibrium system? In the dissociation equilibrium system, the H plus ions are now decreased because this OH minus ion are combining to form water molecule, and in order to restore the concentration of H plus ions in the solution, the acetic acid starts to increase its dissociation. This is because of the Le-Chatelier's principle. This is in accordance with the Le-Chatelier's principle. Okay, and this is again how the pH of that buffer solution does not change. So this is how we have seen when we consider the mechanism of action of acidic buffer. When we consider the mechanism of action of acidic buffer, that is how this buffer solution is trying to resist its pH value. We considered here an example of acidic buffer. In that acidic buffer, it consists of an equimolar mixture of weak acid, and its salt with strong base. So let us have an example. Acetic acid reacting with acetic acid, an equimolar mixture of acetic acid and sodium acetate. Now in this buffer solution, would be there. There will be dissociation of acetic acid into acetate ions and the dissociation of sodium acetate into acetate ions and Na plus ions. So this is the fate of equilibria present in this acidic solution. Now we are trying to understand what is this buffer capacity or what is action. What is this buffer action? For that we have considered this example. Now buffer action or buffer capacity is the ability of that buffer solution to resist change in its pH value, and how that resistance is shown by that particular buffer that we want to discuss here. Okay, so this acidic buffer will consist of large number of undissociated acetic acid molecules, large number of acetate ions and Na plus ions. So they will be there. These ions and these undissociated acetic acid molecules will be there in large excess in case of this acidic buffer. So if we try to add some acid, means if we are trying to add some H plus ions, so the H plus ions will combine with the acetate ions and they will form this neutral or undissociated these acetic acid molecules, and therefore pH of the solution doesn't change. If we try to add some base to this buffer solution, see the OH minus ions which are added from the base, they will combine with the H plus ions which are present there in the solution. So this OH minus ions from added base, they will combine here with the H plus ions from the buffer solution and they will form neutral water molecules. Okay, and if this is happening, the dissociation of this acetic acid increases to again restore the concentration of H plus ions. Means the concentration of H plus ion is getting maintained. In both the cases, if we try to either add acid or base to the solution, the concentration of H plus ion is getting maintained. And if concentration of H plus ion is getting maintained, it means pH of the solution is remaining constant. This is how this acidic buffer works, right? So we have seen here mechanism of action of acidic buffer. The next point is the mechanism of action of basic buffer, or how this basic buffer resists the change in its pH value. So once having clear idea about the mechanism of action of acidic buffer, the similar analogy can be applied for basic buffers also. So in the acidic buffer, we have seen that this acidic buffer is an equimolar mixture. Acidic buffer is an equimolar mixture of weak acid and its strong salt with strong base. Basic buffer likewise is an equimolar mixture containing weak base, let us suppose ammonium hydroxide, and its salt with strong acid, that is ammonium chloride. Okay, so if we consider this ammonium hydroxide, it is a weak electrolyte, so that it will dissociate to a very small extent because of its weak nature, and ammonium chloride is a salt, it will dissociate to a large excess. So in this buffer solution, there will be a large number of ammonium hydroxide, undissociated ammonium hydroxide molecules. There will be large number of ammonium ions and there will be large number of Cl minus ions. So this buffer solution, which is now here an example that is consisting of equimolar mixture of ammonium hydroxide and ammonium chloride, this buffer will consist of a large amount of undissociated ammonium hydroxide, large amount of NH4 plus ions and Cl minus ions. Now let us look what happens when some acid is added or when some base is added, as in the previous case. So if a few drops of HCl are added, Means if I am trying to add some H plus ions, any acid in general, if I am trying to add some acid, means H plus ions are to be added now in that solution. So the H plus ions from this added acid, they will combine with the OH minus ions from the buffer solution. Okay, the OH minus ions are coming in this buffer solution because of dissociation of that weak base. Dissociation of weak base, that is ammonium hydroxide. So these H plus ions from added acid, they will combine with the OH minus ions from the buffer solution, and there will be formation of water molecule. And again, in order to restore the concentration of OH minus ions, in order to restore the concentration of OH minus ion, this weak electrolyte will try to increase its degree of dissociation. It will try to maintain the concentration of OH minus ions by increasing its dissociation into NH4 plus and OH minus ions. Now, if a few drops of base is added, if a few drops of base are added, means let us consider NaOH or KOH is added. So if we are trying to add some base, that is say hydroxide base, then what is happening there? The OH minus ions, they will react with this NH4 plus ions. They will react with these NH4 plus ions and they will form undissociated ammonium hydroxide molecules. So in both the cases, what is happening? In both the cases, what is happening? If we try to add either strong acid or strong base, a little amount of strong acid or strong base to this buffer solution, which is basic buffer in this case, it is trying to maintain its pH value. It is trying to maintain its H plus ions. It is trying to maintain the concentration of ions which are already there in the buffer solution. And this is how pH of the buffer solution doesn't change. pH of the buffer solution doesn't change. So in this lecture, we considered what is meant by a buffer solution. A buffer solution is nothing but a solution which tries to resist change in its pH value on addition of a small amount of acid or base. We have considered this human blood as a natural example of this buffer solution. Now, we have also seen what are the two types of buffer solutions. There are two types of buffer solutions. One is called acidic buffer solution, another one is called basic buffer solution. An acidic buffer solution is a buffer solution consisting of equimolar quantities of weak acid and its salt with strong base. And for this acidic buffer, the pH range for this acidic buffer is in between 0 to 7. The pH of this acidic buffer is calculated by using the Henderson equation, that is called pH is equal to pKa plus log of concentration of salt upon concentration of acid. That is for acidic buffer. And basic buffer is nothing but a buffer solution consisting of equimolar quantities of weak base and is salt with strong acid. Let us consider an example, that is ammonium hydroxide and ammonium chloride. Now this pH of this buffer solution will be in the range of 7 to 14. Actually, pOH is to be considered there because it will consist of quite a good number of OH minus ions. Now the pOH of this basic buffer is calculated by using this relation, that is pOH is equal to pKa plus log of concentration of salt upon base. You are saying that we have discussed their pH in case of acidic buffer and we have considered their pOH in case of pOH basic buffer. Now how to calculate the pH? From this very simple relation, we can calculate it from, that is called the pH plus pOH is equal to 14. Okay, so once you determine either pH or pOH from a solution, you can find the other quantity from that particular solution. And buffer capacity or buffer action is nothing but buffer capacity is nothing but the mechanism how the solution is trying to change how the solution is trying to change its pH value, how the solution is trying to resist change in its pH value on addition of a small amount of acid or base. In the mechanism of action of buffers, we have discussed about the how this acidic buffer works. For this purpose, we considered a simple example of acetic acid and sodium acetate. So in this acidic buffer, it will consist of a large amount of undissociated acetic acid molecules, large number of acetate ions and Na plus ions. And what will happen if we try to add some acid or base? In both the cases, either in acidic buffer or basic buffer, the concentration of the ions which are already there, they are trying to maintain the pH of the solution, and that's why pH of the solution tries to remain constant, and therefore we say that buffer solution